Hello everyone. So we have two guests today. We have a guest lecturer, which is David Vaccaro, and we have a very brief guest speaker. Sean is the designated safeguarding lead. So a quick intro from Sean, and then we'll continue with David.
Yes, hi. I'm just dropping in to say hello, to introduce myself. So yes, I'm Sean. I've been in the Department of Physics for about 12 years now, so I've been around for a long time. Part of my role is just to ensure that all the young people we work with are sort of safe and happy. So that's what I'm introducing myself as, really. So as designated safeguard lead, if you want to contact me at any point, if you've got any concerns about your welfare, you're not feeling very happy with anything, you can get in touch with me. There's also lots of excellent people you're working with, so you can talk to your tutor if there's anything you wanted to talk to them about, and they will contact me. There is also Vlad and Rachel, who are also trained as safeguarding leads as well. So they are good people to talk to if you have any concerns about your tutors or anyone in your group. So there's lots of people out there that can hopefully help you get the help you might need. So that's it really. You will see me again. So I will be popping into your tutorials. I'll probably do that in the new year. And that's just to see that everything's running okay. So my plan is to get to visit all of them, and it's really a nice thing to do because I can see how hard you're all working. So yeah, expect to see me there. What I'll do, I will say goodbye now, but I will write in the chat my email and you can contact me anytime. Okay, thanks and good luck.
Thank you, Sean, and to you, David. Oh, nice, Mo.
A nice Movember moustache. Fine, we're there. Sorry about that. Okay, so I'm going to work through some of the problems on the differentiation sheet, and I think it'd be really good to reach some of the later problems. But before we do that, I think it'd be really useful just to look again at some of the ideas around differentiation by first principles. So let's consider the following function. So let's consider the function x squared minus a squared divided by x minus a. So can anyone in the chat tell me what this function is equivalent to? Can anyone simplify this? So I've got this lovely fraction, x squared minus a squared over x minus a. Can anybody in the chat tell me what it simplifies to? Right, excellent. So everyone is awake and everyone is some people even putting question marks. This looks so straightforward, right? That this is just equal to x plus a, right? So if I was to plot this on a graph, and again, I just want to see if people are awake, what would the graph of y equals x squared minus a squared over x minus a look like? So, right, everyone is saying a straight line, but someone in the chat, Charlie, has said a doesn't equal x. So the really interesting fact here is that this identity statement is not quite valid. This identity statement only holds when x is not equal to a. So what you actually have here is a straight line, and then depending on the value of a, there's a little hole in it. Right, what is the y value of that hole? Well, obviously, if we substitute a into the left-hand side, we just get a math error. But if we substitute a into the right-hand side, there's absolutely no problem at all, the y value is just equal to 2a. Okay, again, answers in the chat, and I think this is a, I think this is a useful skill of sort of changing, well, being able to sort of look at a function and sort of see what it represents. So this fraction here, x squared minus a squared over x minus a, what does that fraction represent? Okay, now it's clearly got something to do, and I'll give you a clue, but the clue is staring us in the face. It's clearly got something to do with this function y equals x squared. So what does this fraction x squared minus a squared over x minus a represent in relation to the graph of y equals x squared? Well, let's try and help ourselves by drawing the graph of y equals x squared. If I take the fixed point A, which is the same A as over here, I get the point a squared. If I take the general point x squared, then I can, from this graph y equals x squared, create all the terms in that fraction. So the x squared minus a squared is just this change in vertical height, which physicists might like to write as delta y. The x minus a is the change in the x coordinate between those 2 points. So that is delta x. And so my mystery fraction up here, x squared minus a squared over x minus a, is just the gradient of the chord, which we could write as delta y over delta x. So if we take any 2 points on the curve, we can calculate the gradient of the chord. Sorry, if we fix the point a squared and then we pick another point on the curve, we can get the gradient of the chord. With that in mind, and again, this is why I really want people to use the chat, just to prove that you're all awake and prove that you're all concentrating. So with that in mind, if this graph here, y equals x squared minus a squared over x minus a, is my delta y over delta x, the gradient of my chord, why is there a hole at x equals a? What does that hole in this graph represent in terms of the gradient of the chord? Yeah, so when delta, there's 2 brilliant answers almost simultaneous to one another. So one of them said delta x equals 0, okay? And that obviously creates a kind of syntax error in this division. We can't have delta x equals 0. The other thing which came into the chat simultaneously was they said tangent, okay? Because when delta x does equal 0, we're trying to take the second point as the same point as the first point. And that sort of, geometrically, or, it's not an allowable operation, but in the limit, as the 2 points get closer and closer together, the gradient of the chord gets closer and closer to the gradient of the tangent. So as we get closer and closer to this hole, the y value is the gradient of the chord. So that must be getting closer and closer to the gradient of the tangent. So this 2a must be the gradient of the tangent. Okay. One of the things I think is quite useful in this sort of webinar setting is just to get you used to like posh vocabulary, posh terminology, the sort of terminology you'll meet in your later studies. So what we would refer to is we would refer to x, the function y equals x squared minus a squared over x minus a at the point x equals a has what is called a removable singularity. So it has a singularity, which is just a posh way of saying we can't plug the number into the function. But it's a removable singularity because we can define the value of the function in a sensible way, which makes the function continuous. Okay, so the key observation here is in that original identity, this right-hand side does make sense when x equals a. So this x equals a here makes perfect sense when x equals a. Okay. The thing which is really nice is that this method, you can just adapt it to to any polynomial. So for example, if I was to play a similar game with x cubed minus a cubed divided by x minus a, and again, I want proof that people are awake in the chat. Who can simplify this this fraction for me when x does not equal a? Very good. Okay, someone was quick. Yeah. Okay, lots of suggestions for x squared plus ax plus a squared, which you can get from polynomial long division. You can also think of it as the sum of a geometric series if you're so inclined. But again, we can just play exactly the same game. That the right hand side makes sense when x equals a. So what does the right hand? If we just take the limit as x goes to a, the limit on the right hand side is completely unproblematic, because what does that box converge to as x goes to a? It just goes to 3a squared. Okay, so I'm sure your teachers at school, if they're good teachers, will have shown you sort of differentiation by first principles by some way or another. I quite like this algebraic way. You can sort of generalize to show that every polynomial is kind of differentiable in this way. You've probably studied quite recently the remainder theorem. So you can always divide any polynomial as a quotient and a remainder, and the remainder is the value of the polynomial at a. If we rearrange, we get a fraction, but on the right-hand side, we just get a nice simple polynomial, and that's going to converge to QA as x goes to a. So nothing, this is just what you will have seen in disguise, but I think it's just quite nice to see a little bit of theory. Right, we've done a little bit of theory. Let's move to problems. Okay, so the first problem that I had prepared, and the first problem which I wanted to go through was, where was it? It was a really nice one. Ah, yeah, it's this one, problem 15. And it says, find the minimum / maximum of f of x is equal to x plus 4 upon x. So in the style of this sheet, so this is part A. In the style of this sheet, the natural way to do it would be through differentiation. So we simply differentiate. So we get our f dash x function. F dash x is the x differentiates to 1. The 4 upon x, it's probably more convenient to write it as 4 times x to the power of -1, which when we differentiate it goes to -4 times x to the power of -2. And which we can write as 1 minus 4 over x squared, which we can write as x squared minus 4 over x squared. Now, one thing which I always like to do, okay, and I know this is a differentiation sheet and there's going to be plenty of sheets later on about curve sketching, but I just always like to sketch a curve because until I sketch a curve, I don't fully understand it. And so what I would always like to do here with my function is, having found the derivative, just think about when it's positive and negative. So I can see that the denominator x squared is always positive. So the sign of the derivative is determined entirely by the x squared minus 4, by the x squared minus 4 question, numerator. So let's think about when that changes sign. So if I was to sketch y equals x squared minus 4, I just get a lovely parabola. The roots are easy to spot at 2, 0 and minus 2, 0. And so what I can see is that x squared minus 4, if x is less than -2, x squared minus 4 is positive. Between the roots, it's negative, and beyond the roots, it's positive. So my function has got a positive gradient up to -2. The gradient is then 0. It's then got a negative gradient. It's then got a 0 gradient at 2, and then it goes up. Okay, so this turning point at -2 is what type of turning point? Put it into the chat. So at x equals -2, we have what type of turning point? It's gone up, flat, down. Brilliant, people are still watching. This is a maximum. Then at 2, it's gone down, flat, up, so it's got a minimum. And now we're going to see if people are really awake. Let's find the coordinates of the maximum and the minimum. So I've got a maximum at x equals -2. And if I go back to my y value, sorry, if I just calculate the function at -2, I get -2 plus 4 over -2, which is -4. So I've got a maximum at -2, -4. And now I've got a minimum at x equals 2, and f of 2 is just 2 plus 4 over 2, which is 2 plus 2, which is 4, which is 2, 4. And now let's just check who is awake. We've got a mystery. Okay, I've drawn the sign of my derivative here. So in this diagram, in this table here. and I've got a maximum at -2, -4. And I've got a minimum at 2, 4. So I've got a maximum that's higher than a minimum, because the maximum has got a y value of -4, and the minimum has got a minimum y value at 4. How do I resolve that how do I resolve that mystery? Okay, so I've got a suggestion in the chat. Someone says they're both in different branches of the graph, and they've said quite rightly, because it's a hyperbola. So why, if we go back to the equation of my graph, so if I go back to my expression for f of x, why are there these two branches? What is the problematic, what is the problem that means that the graph doesn't look like this down and up? Yeah, the 4/x, and in particular, what value of x creates problems for the 4/x term when x equals 0? Excellent. So the signs of that derivative, so that yellow highlighted up, flat, down, flat, up, is correct. But what happens is something funky happens at 0. And so the graph really looks like this. It does have a maximum at -2, -4. But that's not a global maximum, that's a local maximum. It then goes down to a vertical asymptote at x equals 0. And then it comes out the other side and has got a local minimum at 2, 4. Okay. Now, computationally, this question is not especially, is not especially difficult, and in some ways you could easily fly by a question like this, because you could just do the question like this, differentiate it, find the turning points, and then classify them by looking at the derivative, but not really think about the shape of the curve. And on later sheets we'll look at curve sketching in much greater depth, but I just wanted to include that here. Actually, this is not a hyperbola, because it's x plus 4/x, so I won't explain what a hyperbola is. A hyperbola is a type of graph that we'll meet in the later curve sketching sheets. Right, got a challenge for you now, everybody. Okay. And I know we're doing differentiation this week, okay, and we will hopefully do lots of differentiation. We've done some in this question. But what I'm going to do now is I'm going to take this problem again. I'm going to go to the big switch in the sky. And it's very useful to do this from time to time. Okay. And I'm going to take the calculus switch. Okay. And I'm going to turn the calculus switch off. Okay. So what I would like from the chat, what I would like people to think about, and I think it's really interesting to compare, is how would I find the position of this minimum at 2, 4 of the graph, of the function x plus 4/x, if calculus were turned off? So we're trying to find the maximum for x greater than 0 of x plus 4/x. Very good suggestion. We could try and plot it. Okay. And if you do a table of values, well, 0 is just obviously blows up. 1 goes to 5. 2 goes to 4. 6 goes to why have I gone to 6? 3 goes to 3 plus goes to 4 and a third. 5 goes to, sorry, why have we gone to 5? 4 goes to 5. 5 goes to 5 point something. So by I, you know, on the whole numbers, the minimum value is 2,4. There was no guarantee the minimum was going to be at 2,4. But plotting, you know, plotting to gain some numerical insight into functions is something which one should do. Here's a nice suggestion. Could you complete the square? Right. So I like this suggestion. So Neil in the chat is talking about squaring. Okay. And squaring is always a good way of finding extremums, maximums, minimums, because it doesn't always work because some functions just get too meaty and too hairy. But we know that if we've got a bracket squared, then it's always going to be non-negative. And if we can sort of force it to be 0, then it would have a minimum. So what could we square? So this is like what people had to do before Newton came along and invented differentiation. And this, I wanted to show this as a contrast between, you know, the calculus on world here of finding derivatives, finding turning points, and then the calculus off world that we're about to see here. So what squared gives me something like x plus 4 over x? Okay, well, to get an x term, I probably need to square root x. To get a 4 over x term, I would probably need to square root something like 2 over root x. But this equality here, at the moment, isn't true. At the moment, this is a near miss. Okay, so it's got a couple of terms that we like. It's got the x and the 4 over x. But what happens when I really square root x plus 2 over root x? Yeah, excellent. Because when I really square this, I also get the mixed term, which is 2 lots of root x times 2 over root x. So I also pick up a 4. Okay, so my function x plus 4 over root x is equal to root x plus 2 root x squared I've written the wrong thing here. Oops. Minus 4. Okay. Does this help? Okay. So, well, this sort of looks like it helps because it shows that x plus 4 over root x, sorry, x plus 4 over x is greater than or equal to negative 4. Yeah, because this term is positive. We then try to force the bracket to be 0, so we get root x plus 2 over root x equals 0, which rearranges to make x root x squared is equal to -2. Has this achieved our aim? Has this worked nicely? Well, we've got equality, but only when a squared term is -2, which is impossible. So someone said, is there some kind of erroneous thing happening? Okay. So this is not erroneous, okay? This is true. Okay, this thing in green. But the problem is, I've completed the square, which Neil told me to. Okay, I'm hoping to get a minimum when this bracket that has been squared is 0. But this bracket that is being squared, unfortunately, is never 0. So I need a bit of a fix. Can anybody think of a fix? And good. Okay. It was very natural here to use the plus inside the bracket. Okay. But that later on led to a bracket that was never equal to 0. So what would have been better was if I used a minus sign. So if I'd done root x minus 2 over root x all squared, then I would have got x when I square the root x term. I would have got 4 over x when I squared this term, and then my units term would be -4. So what I get here is x plus 4 over x is equivalent to root x minus 2 over root x. Squared plus 4. Okay, and now this is going to be much, much better because this has got the right minimum value. This has got the right minimum value of 2. Okay. Because what we can see here is that we can make a minimum when this bracket that we're squaring is 0. So when this bracket is 0. So what we've got here is x plus 4 over x is greater than or equal to 4, with equality if and only if root x minus 2 over root x is equal to 0, which implies x equals 2. And this is only valid for x is greater than 0 because I'm taking square roots. Okay, so it's interesting to compare the calculus. This is the calculus-free method, or this is a calculus-free method. Okay. And I think you'd agree that the calculus-free method is kind of pretty, but also requires a lot more brain work. Out of interest, does anyone recognize this? Has anyone seen this inequality? Has anyone seen this inequality before? Does anyone want to give this inequality a little bit of a name? Well, if I was to just generalize, okay, I've got that A, okay, I won't. If I just generalize, I can do something similar. I can say root A minus root B all squared is equal to A plus B minus 2 root AB. And then if I say that the thing on the left is greater than or equal to 0, I get that A plus B is greater than or equal to 2 root AB. And I get that A plus B over 2 is greater than or equal to root AB. So this is a generalization. And this is quite famous. This is called the AMGM. It's called the AMGM inequality. Excellent. Okay, I'm going to return now to the chat to something which was said earlier about what I did earlier when I did differentiation by first principles. I convinced you here that I could differentiate any polynomial. But the question came up in the chat about what about sine and cosine? So let's do this from a more physicsy point of view. Okay. If I and it's up to you to decide whether this is first principles, okay, or whether this is intuitive. But I really, really like this argument, and I know a lot of you are physicists. So I think this is quite nice physicsy way of thinking of it. So I've got a unit circle. Okay. I want you to imagine that you go round the unit circle starting at 1, so at time 0, you're at the point 1, 0. And you go round the unit circle with speed 1. Okay, now I'm going to test you all, see if you're all awake, see if you're all listening. And I'm going to ask you, what is your position at time t? Let's go into the chat. I want to... Okay, so I've got someone's awake. Well done, Neil. Someone else is awake. Well done, Sanjbati. Well done, Jessica. Lots of people are awake. That's good. Teachers love it. Right. Now, right. And someone said something important. Okay. And I think this is a really good example to see why radians. Okay. So what's coming through from the chat is people are saying cos t, the position is cos t sine t in radians. Okay, so let's work out why. So first of all, at time t, this angle here I'm going to call theta t. Okay, Now this obviously, because I'm going at a unit speed, so like picture a sort of turntable, theta t is just going to increase as a straight line. Okay, so theta t is just going to be some k times t. The radius of the circle is 1. So just very simple trigonometry, the base of this triangle, let's try and get a nicer coloured pen, is just the adjacent of this right angle triangle. So this length down here is cos theta. This height is just the opposite of the angle theta. So this height is sine theta. That's just trigonometry. Now, what is theta? Okay, now we go at speed 1. Okay, so at what time so at what time do we go all the way around the circle? We go all the way around the circle at time 2 pi. So what we know is that theta of t is equal to kt. And we know that when t is 2 pi, theta t is like a whole revolution. Okay, so one whole revolution is equal to 2 pi k. Okay, now what we really want to do here is we want to choose our angle measurement to make everything as simple and as nice as possible. Okay, so the nicest, we don't really want a k flying around. The nicest value of k would be k equals 1. Now, if k equals 1, then the value of theta for one whole revolution is equal to 2 pi. And I think this is a really natural way for radians to emerge. Okay, so here the radian emerges as the angle that you get if you just go around the unit circle at the unit speed, and the angle is equal to the time. Okay, so for example, when t equals 1, I've gone around an arc of length 1, and so the angle here is the angle, so this is time 1. The angle at time 1 is the angle which subtends an arc of length 1, because I'm just going around at a unit speed. But that is exactly the definition of a radian. So the definition of because the definition of 1 radian is the angle which subtends an arc length of 1. So Neil's put something into the chat. I recommend everybody going into the chat. So Neil has said, isn't that circular reasoning though? Aren't you defining the 1 revolution is 2 pi at the start? No, it's not circular. It's not circular reasoning, okay? Because there's an arbitrariness about our unit of measurement for angles. Okay, so we could have worked in degrees, we could have worked in 360 degrees. But what there's not an arbitrariness about is there's not an arbitrariness about the length, the length around the unit circle. The length around a unit circle of 1 meter is 2 pi, is 6.2 and a bit meters. Okay, so if you run around a unit circle at speed 1, it's going to take you 6.2 seconds to go around the unit circle. Okay, so there's nothing arbitrary about the 2 pi being the distance around a circle. Oh yeah, okay. So what Neil now said is, I get that, but I said you're referring to t equals 2 pi and hence k equals 1. Okay, that's not circular reasoning. It's reasoning from a point of view of mathematical convenience. Okay, so there's an arbitrary choice, and there's always going to be an arbitrary choice about which angle measurement we use. Okay, but from a point of view of mathematical convenience, okay, I'm just going to say I'm going to use the angle measurement that makes k equals 1, which just makes the angle equal to the time. Okay, and we'll see why this is a particularly sensible thing to do, because it makes differentiation work. And that's the real reason why, you know, your maths teacher is probably telling you from now on you're going to use radians more and more. Why you use radians at A-level work and beyond is because radians is what makes calculus work, makes differentiation work, exactly for this example. Okay, so yeah, so what we find is that if we measure in radians, then the angle subtended at time t is just equal to t, and the position is cos t sine t. Okay, now another question to the group, again to check if you're awake. The question now is, okay, so we're going around the circle. We know that at time t, we're at this point, and we know that our speed is 1. What is our velocity? So if you're going around a circle, in what direction is your velocity? Excellent. Okay, if I want to go around a circle, at any point, I need to go tangential to the. I need to go tangential to the circle. So at any point, my velocity, and if I'm going around anti-clockwise, I'm going this way. But at any point, my velocity is tangential to the circle. So this is the tangent. Now, what do we know from basic geometry is the relationship between the radius and the tangent. They're perpendicular. Right, so the radius vector is cos t sine t, and this is length 1. So this is my radius vector. My velocity vector is also length 1. Okay, but is perpendicular to my radius, but they're the same length. So the radius and the velocity are the same length, but perpendicular. Okay, so now if I draw vector 1, and then I'll just do this general. So I'll just call this V1, and I'll just call this AB. What geometric transformation do I need to do to V1 to make a vector that is the same length but perpendicular? So if I want to turn this vector, v1, into this vector, v2, I need to rotate by 90 degrees. Okay, now if I rotate by 90 degrees, and I probably should have drawn it a little bit less square. Actually, I'm going to draw it a little bit less square because my A and B are a bit too close together. But if I take the vector A, B, and I rotate by 90 degrees, what was across becomes up, and what was up becomes across and left. So the vector AB goes to the vector minus BA. So my radius vector is cos t sine t. My velocity vector is length 1 and perpendicular. So it's a rotation by 90 degrees. So I just need to do this transformation over here. So if the A and B had been cos t sine t, then it would become minus sine t cos t. So my velocity vector, and again, I'll leave it up to you if you think this is rigorous, if you think this is hand wavy or not, but my velocity vector is minus sine t cos t. Okay, now again, I'm going to put a question to the chat to see if people are awake. My position vector is cos t sine t. My velocity vector is minus sine t cos t. Because it's the same length, because it's unit radius, unit velocity. Okay. And now my question to everybody is, what mathematical operation, and as physicists, this is crucial, what mathematical operation is it that takes position to velocity? Yes. People are awake. People are contributing in the chat. People know. People get this. Okay. Because if I was going to get the velocity, I would look at my initial position, so my position at time t. I would then look at where I've moved to. So I look at my position at t a little bit later. I would then look at my displacement over that interval, so my change in position. And then if I divide by but if I want to get my average velocity over that interval, I do change in position over change in time. As delta t goes to 0, this side goes to the derivative of the position. This side, we decided that the limit of the change in position over the change in time is the velocity. So the velocity is the derivative of the displacement. And you can convince yourself that if you differentiate, you just differentiate component-wise. You just differentiate the x component and the y component, and you'll see that in the physics sheets, I'm sure. So what we know is that this geometric argument that takes me from cos t sine t to a velocity of negative sine t cos t is just differentiation. So cos t differentiates to minus sine t, and sine t differentiates to cos t. There's, of course, more geometric based arguments with trigonometry and small angle approximations and stuff like this. But I really like this example for two reasons. One, it's much less messy, and two, it really brings home in this point here, this section here, the operation where we made the angle equal to the time, and this was the conversation I had with Neil, really. This is the answer to y radians. Okay. Quite an important example, quite a lot to process there. Does anyone have any questions about that, or are people good? Are people happy? If you're happy, put a thumbs up in the chat, and I will continue. If you've got a question, put the question into the chat. Super. At least 3. Okay, Raghav's asked, so how would you find the maximum in the pre... Oh, that's a good question. So Raghav's question, he was clearly happy with this bit, okay? He was clearly happy with the calculus approach. But he said, when I did the calculus-free method, I needed to restrict to x greater than 0 so I could have my square roots. But then I never went back, and thanks for pointing this out to me, Raghav. I never went back and looked at what happened when x is negative in the calculus-free approach. Now, what kind of mystical, magical, or important idea comes to my aid? So the calculus-free point version has made me at least understand that I've got the minimum at 2,4. So I know that I've got a picture that looks like this, a minimum at 2,4. I know that y is equal to x plus 4 over x. What can I notice that is going to come to my aid in order to get this, to be able to realize that I don't really need to do any work for the negative x? And again, this doesn't always happen. But if I replace x by negative x, then y is equal to negative x plus 4 over negative x, which is the negative y value. So what that means is that if I've got a point on the graph up here of x, y, the y value at negative x is equal to negative y. Now, what geometric operation do I need to do to turn, let's do it with vectors because you're physicists and like vectors, to turn this vector xy into this vector negative x, negative y? Well, I just need to rotate by 180 degrees. So if I just rotate this curve by 180 degrees, then I get the curve here. Okay. So this negative curve or the curve when x is negative is just the same curve when x is positive, but just the same but different. And notions of being the same but different is something which just becomes more and more and more important when you do more mathematics and more physics. We call symmetry. Okay, so the fact that the maximum is at -2, -4, if you're going to do it by a calculus-free approach, we've solved it in the positive quadrant. We know that it's got this odd, what this symmetry is called an odd symmetry. And so the maximum for negative x is just the maximum value you get when x is negative is just the negative of the minimum value that you get when x is positive. And Neil says, is there a way of telling when a function is an odd function beforehand? Yes, there is, Neil. And it's quite nice because it tells you where the word odd comes from. So if I was to write y equals x plus 4 over x in power form, it's x to the 1 plus 4 times x to the -1. And if I look at these powers, 1 and -1, they are both odd numbers. Now, more generally, a power function like y equals x cubed looks like this and is odd. A power function like y equals x squared looks like this and has even symmetry. So basically, if the powers are all in the polynomial are all even, then the function has got an even symmetry. If the powers in the polynomial are all odd, then it's got an odd symmetry. And I'll just give you a little appetizer. The graph of y equals sine x looks like this. Okay. And this has got an odd symmetry. So it's a weird idea, okay? If sine x were a polynomial, then it would have only odd powers. Okay. But I'll just leave this hanging. But surely sine x is not a polynomial. Or is it? Okay. And much, much, much later, we will see that sine x really is a polynomial. Sine x is not a polynomial. Okay. Sine x is, however, like all kind of our famous nice functions, an infinite polynomial of something which is called a power series. And if you write sine x and cos x as power series, and you know the theory of power series, you can resurrect some of this sort of arguments. I'm getting sidetracked into concepts. Right. I feel like I really need to look at problems. Otherwise, Vlad's going to sack me. Vlad's going to say this webinar didn't look at any of the problems on the problem sheet. So let's look at the problems on the problem sheet. And the next problem I really want, I really want to do 2 more problems. And the next problem I really want to look at is problem 16. And so this is the one which says, find the shortest distance between points on y equals x squared and points on the line y equals 2x minus 2. Okay. This is a brilliant question. Because what's going to happen here is, and this, the more of the advanced questions you do, and when you do questions from PAT papers, MAT papers, things like that, this happens all the time, is letters are going to temporarily change we subtly need to sometimes treat things as a fixed constant, and then we need to suddenly shift our perspective and view them as variables that can change. So let's first of all draw the picture. So we've got the line, sorry, we've got the curve y equals x squared. Oh, by the way, there's also an easy way of doing this question. Okay. And the easy way sidesteps a lot of the algebraic grind that I'm going to go through, but I'm going to show you the algebraic grind because I think it's important, to see how that works before just seeing the we could have avoided it all if we'd been smart. So here's our curve, y equals x squared. Here's our line. Now we need to pick a point on the curve. So I'll call that A, and I'll call that A squared. Then I need to take a point on the line, and I'll call that B, and then the y coordinate is 2b minus 2. Now, if I do it completely the hard way, I could do it like this. I could look at the distance AB. And I could say that by Pythagoras, AB is B minus A squared plus 2b minus 2 minus A squared all squared. And then I get b squared minus 2ab plus A squared plus 4b squared minus 8b minus 4ba squared plus 4 plus a to the 4. Right, now this is horrible. Okay, now what we want to do is we want to vary a and b. Okay, and make this as small as possible. Now, this function, I'm going to do varying layers of doing clever stuff. Okay. Because if a problem hadn't been amenable to the really easy solution, you might have needed to do it the hard way. And if you're doing the hard way, you should always be looking for the slightly easier way. The first thing I noticed is that as a function of A, this is a quartic. As a function of B, this is just a quadratic. Okay, so it's going to be easier to fix A and then find the value of B that makes minimum. So I do AB squared, and this is equal to 5B squared. Now I need to be a little bit, I need to gather my terms. So minus 2A plus 4A squared B. Oh no, there's a minus 8. So plus 8B plus A squared plus 4 plus A4. And someone's putting in the chat something which I know, okay? And they're putting in the sort of easier way of doing this, okay? So I try and think of it yourself before you look at the chat. Okay, so what if I use calculus, and there becomes a little bit of a temptation to always use calculus because calculus is such a great tool, okay, that why would we ever do the calculus free way? So if we use calculus, we could differentiate with respect to B, treating A as a constant, and then try and find the minimum value of B. Okay, so if we differentiate with respect to B, we get 10B minus 2A plus 4A squared plus 8. And then we set this equal to 0. This is a 10. So we get B is A plus 2A squared plus 4, I guess, all over 5. Okay. But there is a better way. Okay. If I'm at this point, okay, think about your mum or dad telling you when you're a child how to cross a road. That if you want to cross a road, you do it perpendicular to the pavement, because then you're minimizing the distance that you're in the road. So if this line is the pavement and you want to cross to A, you just do it at the point which is perpendicular. So much nicer than calculus is just to say that we could find B by noting that this gradient is perpendicular to the 2x minus 2. So the gradient is negative a half. Okay, so what we could do there, and the working would be easier, is we just get the line through A, which has got gradient negative a half, which is y minus a squared equals minus a half x minus a. That's just my change in x times the gradient is equal to the change in y. And then we find the intersection of that with the line y equals 2x minus 2. And to get the x coordinate, we can just equate the expressions for y. So we get 2x minus 2 is equal to a squared minus a half x plus a half a. And then with no calculus or nothing fancy, we just get 5 halves x is equal to a squared plus a half a plus 4. And then when we multiply by 2 and divide by 5, we get the value of x is just again 2a squared plus a plus 4 all over 5. That was a plus 2 there. Okay, so we get the same, but here, calculus free turned out to be better. Okay, so we now know the value of, for a given value of A, we know the value of B, which makes the distance shortest. So all we need to do is substitute that value of B back into this expression. Okay, and if we substitute that value of B back into that expression, we then get an expression in A that we can then solve, that we can then use calculus, and then we can solve it, and it all comes out. And I'm a little bit short of time, but I'll leave that as an exercise. But can anybody spot the most intuitive, the best way of doing this question? So let's say that we do this thing of, we know that AB, we know that for a given A, we want to go perpendicular to the line. I'll do it at this point because I think this is kind of where it's obvious. So here, if I look at the origin and I go to the point on the line, I'll call it B dash. This line segment is perpendicular to the line y equals 2x minus 2, but it's not perpendicular to the curve, because that would be horizontal. So from the perspective of the curve, yeah, if I was to go a little bit this way along the curve, I would shorten the distance. If you get a good geometric intuition, you should convince yourself that the point that you're looking for is a point which is, yes, perpendicular to the line, but also perpendicular to the curve. So also a normal to the curve. Because if we were at that point, let's imagine we've got two children wanting to cross the road, one at A crossing to B and one at B crossing to A. The child at B crossing to A, we know will go perpendicular to the line. The child at A crossing to B, if he goes a little bit along the curve, so if he goes a little bit along the tangent, he goes to a point which is essentially here. I'm a little bit messy, my diagram. But in moving along this tangent, he's now crossing via this hypotenuse. Whereas if he goes the other way, he's now crossing along this hypotenuse. So either side of A would be bad. So if he moved away from A, there'd be a longer crossing point. So the really slick way of doing this problem that sidesteps a lot of algebra is to notice that we're looking for the point on the curve A where the normal to the curve is also perpendicular to the line y equals 2x. So if we do that, we've got the curve y equals x squared. We've got dy by dx is equal to 2x. And this is normal so that's the gradient of the tangent. The gradient of the normal is minus 1 over 2x. And then this is perpendicular to y equals 2x minus 2 when its gradient is negative a half. Okay, so this minus 1 over 2x is the gradient of the normal. And that's perpendicular to y equals 2x minus 2 when that gradient minus 1 over 2x is minus a half. But then we just solve minus 1 over 2x is equal to minus a half when x equals 1. So then the point on my curve is the point 1, 1. And then we just look for the point on the line y equals 2x minus 2, where that's perpendicular. So we get y minus 1 is minus a half x minus 1. So we get y equals minus a half x plus 3 halves. And we find the intersection of that with y equals 2x minus 2. So we get minus a half x plus 3 halves is equal to 2x minus 2. So we get 7 over 2 is equal to 5 over 2x. So x equals 7 over 5. So this point is 7 over 5. And then what do I get? 14 over 5 minus 2. So 4 over 5. And that's the shortest distance between the two. Okay. I was running a little bit short on time. Okay, so sorry, let me answer any questions on this to make sure I get this. So someone said, I didn't quite get it. So basically, we need to find the equation of the line of the normal and find the points from there. Okay, so it depends if you get this insight or not. So normally, the way that I would expect most people to do this question the first time, would be to take a general point on the curve, AA squared, and then to realize that the point on the line that is closest is going to be, you can draw a line which is perpendicular to y equals 2x minus 2 that goes through A. Okay. That line will have gradient minus a half. Okay, so this is the line. This line here is the line through A squared, which is perpendicular to y equals 2x minus 2. If you solve that simultaneously with the line y equals 2x minus 2, that gives you the x coordinate of the point on the line. Once you know the x coordinate of the point on the line, so you've got one point which is a squared. You've got another point which is the point on the line which has x coordinate 2a squared plus a plus 4 over 5. The y coordinate is 2x minus 5, so I just multiply this by 2x minus 2 and subtract 2, so I get 4a squared plus 2a plus 8 over 5, but then minus 2, so minus 2 over 5. So that's the point on the line. And then the long way with calculus is to find this length by Pythagoras. That will give you a polynomial in A that you can then differentiate and find the minimum. Okay. The better way is to notice that the actual point that we're looking for is this special point, is when the normal to the line also ends up being the normal to the curve. Because at that point, the child crossing the road on the curve, if they move along the tangent, they're getting further away from B. So you can sidestep all the calculus by looking for the normal to the curve that is also a normal to the line. So you look for a normal to the curve that has got gradient minus a half. Okay. Has everybody got that, or does anyone still have any questions? Okay, the final question I want to look at is question number 17. Oops. So question 17. Oops. So question 17 says an isosceles triangle has sides x, x, and p minus 2x. What is the maximum area? So we could do x, x. The base is p minus 2x. So this distance is p minus 2x over 2. If I drop a base, sorry, if I drop a perpendicular to the base, then to find the area, I need to find this height. So I say the height is x squared minus, and I'm just going to make life a little bit easier. I'm going to call p over 2, I'm going to call s for semi-perimeter. So it's x squared, the height squared, and this is just Pythagoras, is x squared minus s minus x squared. If I simplify, I get that this is 2sx minus s squared. That's the height. So the height is the square root of 2sx minus s squared. The area is half base times height. The base is p minus 2x, which is the same as 2s minus 2x. And then the height is square root of 2sx minus s squared. So this the area is s minus x times the square root of s in brackets 2x minus s. We want to maximize the area, okay? So it makes sense to, well, we can realize that maximizing the area is the same as maximizing the area squared. So it makes sense to say that the area squared is s minus x all squared times s times 2x minus s. Okay, and that's just going to be much easier to differentiate than this horrible thing with square roots and needing to use the chain rule. So to maximize a squared, I want to differentiate. It probably makes sense to open the brackets first, and if I open all the brackets, I get that this is this expands to 2x cubed minus 5. I did this earlier because I didn't want to get bogged down in the algebra here. 5x squared x plus 4s squared x minus s cubed. And then to maximize, we differentiate and we get 6x squared minus 10sx plus 4s squared. And then the derivative is 0 if 3x squared minus 5sx plus 2s squared is equal to 0. This looks a little bit scary, but it's just a quadratic. And we can factorize this as 3x minus 2s, x minus s. So we get possibilities for x as 2s over 3 or x equals s. Okay, and if you do second derivative test or if you sketch the graph, you realize that it's a cubic. So the maximum is going to be, the general shape of a cubic with a positive x cubed coefficient is this. So the maximum is at the smaller value, so is at this one. This one clearly can't, if you work it through, this one can't be the maximum because this one gives an area of 0. Okay, so what it turns out is that x is equal to 2s over 3. And this is a equilateral triangle. Okay, just to finish, and this is a little bit of a high point for the sort of real pure mathematicians out there. Firstly, just interested to see, does anybody know what result of sort of classical geometry this formula for the area squared is? It's a bit of a general knowledge test. You might know it or might not. Yeah, well done, Akshat. This is called this. You could get this result as Heron's formula. Okay. Is there a calculus-free way of minimizing this product? So we've got s minus x all squared times s times 2x minus s. Now, this is just for the purists out there, okay? For the purists out there, we saw earlier the AM-GM inequality, which said that a plus b over 2 is greater than or equal to the square root of ab. It turns out that this generalizes. So if you add, I don't know, a plus b plus c over 3, then this is greater than or equal to the cube root of ABC. Yeah. Or if you add 4 things, this is greater than or equal to the 4th root of ABC D. And that you get equality only in the case when everything's equal. Okay, so what does, obviously this is like nothing to do with the sheet. This is just a little entertainment for those who love this sort of thing. Here so this expression for the area squared is the product of 4 things. So we know that s minus x squared times s times 2x minus s. It's the product of 4 things but one of them happens to be squared. Oh, wait a minute, no. S is the semi-perimeter, so that's fixed. So the sort of brackets that vary are just the ones with an x in. So s minus x and 2x minus s. But AM-GM tells me that this product is less than or equal to the sum over 3 all cubed. But the thing which happens really nice, if I look at the sum, the minus x, and the 2x cancel. And then I get s plus s, take away s, so I get that this is just less than or equal to s over 3, all cubed. But then the really nice thing is I've now got an upper bound, but I just get equality if everything is equal. So I just get equality if s minus x is equal to 2x minus s. Okay, so, you know, AMGM inequality just tells me that because these 3 brackets that I'm multiplying have got a fixed sum, that 3 terms which have got a fixed sum, and you can actually do a nice geometric argument to see why they sum to the semi-perimeter. The moment you've got 3 things that sum to a fixed sum, you get the maximum when they're all equal. Okay, but when they're all equal, we just get that 3x is equal to 2s, so x equals 2s over 3. Okay, and so this is calculus free. And the nice thing with this is that it didn't actually need the triangle to be isosceles. It would have also worked just if AB and, you know, just if you'd had 3 sides in a given perimeter. So yeah, calculus is good and differentiation is good, but this is an example where the calculus free way actually wins. Okay, so that was a bit of extension. Okay, I hope you enjoyed this webinar. I hope the balance was right. You know, obviously in your tutorials, you'll go through the problems, but I just wanted to give a little bit of theory as well. So if we just look at what we did, we started with the theory of differentiation of polynomials by first principles. We then did an example and we compared the calculus approach to a calculus-free approach, looking at AMGM. We then looked at a little bit of theory and did a sort of physicist's proof of the differentiation of trig functions. We then did the shortest distance problem and noticed the importance of sort of geometric intuition. And then we finished with the isosceles triangle and did a sort of, you know, slightly more high-tech comparison between a calculus approach and a calculus-free approach. Right, I'll just go to the chat. Thank you. Will you be appearing in some more webinars in the future? Yeah, I've got a few lined up. So I hope to see you again. If you liked it, I hope you're looking forward to seeing me again. But yes, I will be doing some. And yeah, lots of thank yous. So yeah, and thank you to all of you as well. So I hope you've enjoyed tonight. And I will see you again sometime soon. Lots more thank yous. I'm not sure if Vlad's going to come back on. I think he might be with his baby. So I'll end the meeting. So goodbye, everybody. I hope that was fun. Hope you learned something. Hope it also helped you get through this lovely sheet. Okay. Good night, everybody.